Right now, for the second time in 6 days, a wall of solar plasma is slamming into Earth's magnetic field. GSU and NOAA just confirmed it. On August 8th, a cloud of charged particles that left the Sun 3 days ago arrived and pushed geomagnetic storm conditions to G2 moderate levels. The KP index, the planetary disturbance scale that runs from 0 to 9, hit 6. That is the threshold where the aurora stops being an Arctic phenomenon and starts pushing into the northern United States. This is not an isolated event. 2 G2 storms in under a week, a G3 storm that lit up 30 states on July 4th, and more coronal mass ejections still in transit show something significant is happening. Today we are going to break down exactly what is happening to our skies, where this is headed, and what it means for the systems we depend on every single day. No guessing, no dramatizing. Just the facts, the science, and the real stakes. If you have ever seen the aurora with your own eyes, especially somewhere it should not have been visible, tell us where you were and what it looked like in the comments. And if you want to understand what the sun is doing to our planet before it shows up in the news cycle, subscribe and hit the bell. We track this so you do not have to wonder. The coronal mass ejection that forecasters suspected would arrive has arrived. On August 8, 2026, NOAA's Space Weather Prediction Center observed G2 moderate geomagnetic storm conditions. A KP6 warning was issued at 1336 UTC, and the official G2 bulletin was published at 2142 UTC. The KP index registered at 6 GSU, a measurement calculated every 3 hours from magnetometer readings at 13 observatories spread across the planet. 0 means the magnetosphere is quiet, 4 means unsettled, 6 means storm. To understand what KP6 actually means on the ground, you need to picture the auroral oval. That is the ring-shaped zone around each magnetic pole where the northern and southern lights normally live. During quiet times, the oval sits near 66 degrees geomagnetic latitude GSO, roughly along the Arctic and Antarctic circles. For every step up the KP scale, that oval shifts roughly 2 degrees of latitude toward the equator. At KP6, the oval has moved about 12 degrees south of its quiet position. In North America, that pushes it well into the northern United States. 18 states fall within the potential visibility zone tonight. Washington, Idaho, Montana, North Dakota, South Dakota, Minnesota, Wisconsin, Michigan, Maine, Vermont, New Hampshire, New York, Pennsylvania, Ohio, Indiana, Illinois, Iowa, and Oregon. People in those states, especially those far from city lights with a clear view of the northern horizon, may see green, purple, or red bands moving across the sky. The source of this storm is a slow-moving coronal mass ejection, a billion-ton cloud of solar plasma and magnetic fields blasted off the sun's surface. Think of it as a cannonball of electrified gas hurtling through space. NOAA's forecasters believe this particular CME likely came from filament eruptions on August 5th and 6th. A filament is a long rope of cooler solar material suspended above the sun's surface by magnetic fields. When it snaps and lifts off, it can hurl plasma into space as a CME, even without a major flare. NOAA uses the word suspected in its official bulletin, which means the forecasting models had difficulty tracking this specific plasma cloud through interplanetary space. The models are good at timing. They are not perfect at identification. The single most important variable determining what happens next is something called the BZ component. This is the north-south orientation of the incoming solar wind's magnetic field. When BZ points southward, it connects with Earth's northward-pointing magnetic field like two magnets snapping together, opening the door for solar energy to pour into our atmosphere. When BZ points northward, the storm may largely pass us by. This one number determines whether a G2 storm remains a beautiful light show or intensifies into something more disruptive. And here's the critical fact most people do not know. We cannot measure BZ until the CME is practically on top of us. The Solar 1 satellite, which replaced the decommissioned DSCOVR spacecraft in mid-2026, is stationed roughly 1 million miles from Earth at Lagrange point 1, giving us 15 to 60 minutes of warning. That is it. Active periods are expected to continue through August 9th, as glancing blows from additional CMEs that left the Sun on August 4th and 5th keep arriving. The magnetosphere, Earth's invisible magnetic shield that deflects most of the solar wind Gisu, is being compressed, distorted, and partially breached. It will not fully settle for at least another 24 hours. But to understand why this matters, why 2 G2 storms in 6 days is worth paying attention to, we need to rewind to what happened 6 days ago, on August 2nd. On August 2nd, 6 days before this storm, Earth's magnetic field was already reeling from another impact. The sequence began on July 30th when active region 4492 XO, a cluster of sunspots rotating across the solar disk, produced an M1.9 solar flare. A solar flare is a sudden burst of X-ray and ultraviolet radiation from the sun. It travels at the speed of light, 8 minutes to Earth. Flares are classified by letters B, C, M, and X, with each letter roughly 10 times more powerful than the last. An M1.9 is a moderate to strong event. That flare triggered something else. Instruments on Earth detected dual Type 2 radio sweeps Jisoo shockwaves moving through the sun's outer atmosphere at 853 kilometers per second and 1,681 kilometers per second. That faster number equals approximately 3.7 million miles per hour Jisoo, fast enough to cross the entire Sun-Earth distance in under 24 hours. The flare also launched a halo coronal mass ejection, a cloud of plasma expanding in all directions from the sun's corona. The CME arrived at Earth on August 2nd at 1759 UTC. Within hours, the KP index climbed to 5.67 and then to a confirmed 6 between approximately 1200 and 2100 UTC. G2 moderate storm conditions were reached. Aurora hunters across northern Scotland and Scandinavia reported visible displays. Power grid operators at high latitudes detected voltage alarms. Spacecraft controllers noted orientation irregularities on several satellites. High-frequency radio propagation degraded significantly above 55 degrees geomagnetic latitude. That boundary, 55 degrees geomagnetic latitude, matters. It is the line poleward of which G2 storm impacts are expected. In North America, that line cuts through the northern United States. In Europe, it runs through northern Germany and Poland. Everything north of that line is in the impact zone during a G2 event. The August 2nd storm produced power grid fluctuations, high-latitude voltage irregularities, and degraded radio communications in those regions. Nothing catastrophic, but noticeable. There is an ambiguity about the August 2nd storm that is worth understanding. Forecasters are not certain whether it came from a slow-moving CME launched on July 27th or a glancing blow from the July 30th eruption. Glancing blows matter because they are harder to forecast than direct hits. A direct hit, CME, is like a head-on collision. A glancing blow is a sideswipe, still capable of generating a storm, but harder to predict in terms of timing and intensity. This ambiguity is not a failure of forecasting. It is a reflection of how difficult it is to track billion-ton plasma clouds across 93 million miles of space. 2 G2 storms in under a week is unusual. But what happened on July 4th, guys, just 5 weeks before this, Jisoo rewrote expectations entirely. On June 30th, active region 4479 produced an X1.1 solar flare. It peaked in minutes and hurled a halo coronal mass ejection into space at approximately 1,496 kilometers per second, over 3.3 million miles per hour. NOAA issued a G2 moderate geomagnetic storm watch. What arrived 3 days later was far stronger. The CME struck Earth on July 3rd, and by early July 4th had escalated conditions dramatically. The KP index climbed past 5, past 6, and hit 7 Gusu G3 strong levels, exceeding the G2 forecast. A G2 storm is moderate, a G3 storm is strong. The difference matters because each step up on the KP scale represents a significant increase in geomagnetic energy input. The Aurora Borealis became visible across more than 30 U.S. states, reaching as far south as New Mexico and Northern California. People in latitudes where the northern lights are essentially never seen looked up and saw green and purple curtains moving across the sky. The reason the forecast missed is the BZ measurement gap. NOAA's primary forecasting tool is the WSA-Enlil model, a computer simulation that predicts when a CME will reach Earth and how hard it will hit. WSA-Enlil is remarkably good at timing. It is blind to magnetic field orientation. Neither WSA-Enlil nor the Solar 1 satellite at Lagrange Point 1 can read a CME's internal magnetic field structure before it arrives. Solar 1 sits roughly 1 million miles upstream in the solar wind. At typical CME speeds, that gives operators 15 to 60 minutes of warning about the BZ orientation. Until that moment, nobody knows whether the incoming plasma cloud will connect with Earth's magnetic field or slide past it. On July 4th, the BZ component pointed southward and stayed southward. The door opened. Solar energy poured in. A G1 forecast became a G3 reality. It was not a failure of skill. It was a failure of instrumentation. A gap that researchers are actively working to close but cannot yet solve. The July 4th event demonstrated that any G1 or G2 watch carries the possibility of escalation if the magnetic field orientation aligns unfavorably. That lesson applies directly to the storm we are experiencing right now. The aurora is beautiful, but the same physics that paints the sky also threatens the invisible infrastructure that modern civilization runs on, and we have data that shows exactly what that looks like. When a geomagnetic storm hits, the first thing people look for is the aurora, but the first thing satellite operators do is check their altitudes. The mechanism is straightforward. Solar energy heats the thermosphere GSO, the layer of Earth's upper atmosphere between roughly 80 and 700 kilometers up, exactly where satellites orbit. When the thermosphere heats up, it expands outward like a balloon. That expansion increases drag on every object flying through it. Satellites slow down, their orbits decay. They start falling. In February 2022, a G1 to G2 storm Jisoo, the same classification as the storms we are tracking this week, Jisoo destroyed 38 out of 49 Starlink satellites in a single batch. SpaceX had launched them into a parking orbit at 210 kilometers altitude, planning to raise them to operational altitude once systems checked out. The heated, expanded atmosphere created enough drag to pull nearly 80% of the batch back down before they could climb. The satellites burned up in the atmosphere. The economic loss was significant. The physics behind it was the same physics operating right now. Even satellites that survive experience massive stress. During that same February 2022 storm, the European Space Agency's Swarm-C satellite recorded a maximum increase in its orbital decay rate of 32.5 times the quiet time rate. Think about what that number means. A satellite designed to orbit steadily suddenly experienced more than 32 times the normal drag. It did not fall out of the sky, but its orbit shifted measurably, requiring corrective maneuvers that consume fuel and shorten the satellite's operational life. The threat on the ground is different in mechanism but equal in severity. Geomagnetic storms drive electric currents through the Earth itself and into anything long and conductive sitting on top of it. Power lines, pipelines, railway tracks. These are called geomagnetically induced currents, or GICs. They can overload transformers, trip circuit breakers, and in the worst cases, collapse entire grids. The defining example happened on March 13, 1989. At 2:44 a.m., a surge of geomagnetically induced current tripped a single capacitor on the Hydro-Quebec power grid. Within 90 seconds, the entire grid collapsed. 6 million people lost power for 9 hours. The direct cost to Hydro-Quebec was $13.2 million Canadian dollars in equipment damage and related losses, with the wider economic impact on the province estimated at several hundred million Canadian dollars. That was a KP9 event, Grosso, an extreme G5 storm, the highest category on the scale. But the physics that collapsed the Quebec grid is the same physics operating at KP6. And the only difference is the intensity of the input. The May 2024 G5 storm Jisoo, the strongest since the Halloween storms of 2003, Jisoo provided a more recent data point. KP reached 9. Aurora appeared from Florida to Mexico, and the economic impact was immediate. Midwestern corn farmers alone lost an estimated $500 million or more from GPS disruption during that single storm. Precision agriculture depends on centimeter-level GPS accuracy to guide tractors, plant seeds, and apply fertilizer. When the ionosphere gets disturbed, those signals degrade. Tractors stop, planting stops, the cost accumulates by the hour. NOAA's economic value studies put hard numbers on what the warning system prevents. For minor disturbances, the electric power industry avoids approximately $111 million in losses by taking protective measures. For severe storms, that number rises to $27 billion. The warnings work. They give grid operators time to reconfigure transmission lines, reduce load on vulnerable transformers, and prepare for the GICs that will flow through their systems. Then there is the scenario that keeps grid planners awake at night. A 250-year geomagnetic storm, Jisoo, the kind that modeling suggests hits Earth roughly once every 2.5 centuries, Jisoo would cause an estimated $2.04 billion per day in U.S. economic losses. It would disrupt power for approximately 5.7 million people and 150,000 businesses. The last storm of that magnitude was the Carrington event of 1859. In 1859, the most vulnerable piece of infrastructure was the telegraph. Today, it is the power grid, the satellite constellation, and the GPS network. All of this, the satellite losses, the grid failures, the billion-dollar economic impacts, happened during storms that were forecastable in principle. Which raises the question, what is the sun doing right now, and what is still heading our way? Solar cycle 25 officially peaked in October 2024. That was 22 months ago. By the textbook, the sun should be quieting down. It is not. The sunspot number GISO, a measure of solar activity that astronomers have tracked for centuries, GISO peaked at 216 in August 2024, far above the original 2019 panel forecast of 115 for the cycle maximum. Even now, in the declining phase, the sun remains capable of producing powerful individual events despite lower overall activity. This is not a minor deviation. It is a significant gap between prediction and reality, and it carries implications for everything we have discussed. The declining phase of a solar cycle is, historically, when some of the most violent individual events occur. Solar cycle 23 provides the clearest example. It peaked in 2001. Over the following years, it produced 10 flares exceeding X10 classification. 4 of those occurred years after the official maximum. The physics behind this pattern is well understood. Sunspot number measures the quantity of activity, not the violence of individual events. The declining phase often features large, complex, active regions. So, twisted knots of magnetic field capable of extreme eruptions even as the overall number of sunspots decreases. The active regions that have been driving this week's storms are cases in point. Active region 4492 produced the July 30th M1.9 flare and the dual-shock CME that arrived on August 2nd. Active region 4479 produced the June 30th X 1.1 flare and the Halo CME that caused the July 4th G3 storm. These regions are rotating back into Earth view as the sun turns on its axis. That means more eruptions may soon be directed our way. The filament eruptions on August 4th and 5th launched multiple CMEs. Some have already arrived. GISO, those are the glancing blows causing the active conditions extending through August 9th. Others are still in transit. NOAA's WSA-Enlil model runs show additional CMEs with expected arrival windows through August 9th and possibly into August 10th. None are currently forecast to produce a major storm. But the July 4th lesson applies here too. The models are good at timing. They are blind to magnetic field orientation. The BZ component will not be known until the plasma clouds reach the Solar 1 satellite, 15 to 60 minutes before impact. The data is already telling us what comes next. More storms, possibly stronger ones. The question is not if, but what we do with the warning. If you are in the northern United States tonight, August 8th into August 9th, you have a real chance of seeing the aurora with your naked eye. Here is exactly how to maximize your odds. Get away from city lights. Light pollution is the single biggest obstacle to aurora viewing. Find a location with a clear, unobstructed view of the northern horizon. The best viewing window is between 10 p.m. and 2 a.m. local time. The aurora often comes in waves, quiet periods followed by sudden bursts of activity that can last anywhere from a few minutes to an hour. Patience is essential. The states with the best chances tonight are Washington, Idaho, Montana, North Dakota, Minnesota, Wisconsin, Michigan, Maine, Vermont, and New Hampshire. But the 18-state visibility zone extends further south. If you live in any of those 18 states, it is worth looking. Monitor the real-time data. NOAA's Space Weather Prediction Center website shows the current KP index and critically the BZ component. The Space Weather Live app and various Aurora alert services push notifications when conditions change. What you are looking for is BZ southward and sustained. That means the magnetic field is oriented to inject solar energy into the atmosphere. That is when the aurora intensifies and pushes south. If BZ flips northward, the storm may suppress, and the lights may fade even if KP remains elevated. A practical tip that has changed aurora viewing forever. Modern smartphones in night mode can capture the aurora even when the naked eye cannot see it. The camera sensor is more sensitive than the human eye to the specific wavelengths of light that aurora produces. If you think you might see something, point your phone at the northern sky and take a long exposure shot. You may be surprised by what the camera reveals. While you are looking up, power grid operators are looking at their screens. They are monitoring geomagnetically induced currents on long transmission lines, especially in Quebec, Ontario, British Columbia, and Scandinavia, the regions most vulnerable to GIC-related disruption due to their geology and latitude. Satellite operators are checking orbital decay rates on their low Earth orbit constellations. They are preparing corrective burns if necessary. The systems are working. Active periods are expected to continue through August 9th. By August 10th, the field may return to quiet, unsettled levels. But the broader pattern is unmistakable. This is a moderate storm. It is beautiful, and for most people, it is harmless. But it is also a reminder, Jisoo, one of several this year, Jisoo, that our star is active, our infrastructure is exposed, and the only thing standing between a beautiful light show and a multi-billion-dollar disaster is the orientation of a magnetic field we cannot measure until it is already here. On March 13, 1989, the Hydro-Quebec power grid collapsed in 90 seconds. A surge of geomagnetically induced current tripped a single capacitor at 2:44 a.m. 6 million people woke to darkness. The outage lasted 9 hours. The direct cost to Hydro-Quebec reached $13.2 million Canadian dollars in equipment damage, with the wider economic impact running to several hundred million. That was a KP9 event, an extreme G5 storm, the highest classification on the scale. The physics that caused it is identical to the physics operating right now at KP6. The vulnerability is the same. The long transmission lines are the same. The geology that channels ground currents into the grid is the same. The difference is that in 1989 there was no operational warning system. Grid operators had no idea the storm was coming until the lights went out. Today, NOAA's Space Weather Prediction Center runs continuous forecasts. The WSA-Enlil model tracks CMEs across interplanetary space. The Solar One satellite sits roughly 1 million miles upstream, watching the solar wind. Grid operators receive alerts. They reconfigure transmission loads, they prepare. The warning system that exists today did not exist in 1989. Both realities coexist. We are more prepared than we have ever been. And the sun is capable of producing a storm that would overwhelm those preparations with very little notice. Every KP6 storm is a test. It tests the forecast models. It tests the grid operators. It tests the satellite controllers. So far in 2026, those systems are passing, but the test is not over. The declining phase of solar cycle 25 will continue producing events. Some of them will be stronger than what we are seeing tonight. The final exam does not come with a study guide. The data is already telling us what comes next. The difference between awe and catastrophe is preparation, not luck. The sun is not doing anything unusual. It is doing exactly what stars do. The question is whether we are paying attention. If you have ever experienced a sudden GPS failure, a radio blackout you could not explain, or a power fluctuation that seemed to come from nowhere, tell us what happened and where you were in the comments. There is a real chance it was space weather, and we want to hear your story. More coronal mass ejections are in transit. The declining phase of solar cycle 25 will continue producing events. We will be tracking every one of them. Subscribe and hit the bell so you know what is coming before it arrives. And if this video helped you understand what is happening in the sky tonight, send it to someone who lives in one of those 18 states. They might look up and see something they have never seen before.